Okay. In the book or in the LH packet, any, this is kind of, well, this isn't our last time of doing U substitution by any means, but this is, we're going to move on to another technique today that you have to be able to do. And so let's see if there's still any issues you have with this substitution method. We got one? 67. What does it say?
The antiderivative of e to the x
Okay.
over e to the 2x plus 2e to the x plus 1.
Like that? Okay. All right. Any ideas on number 67? Let u be the bottom. Okay? Now, thinking ahead, if I let u be the bottom, the du is going to be 2e to the 2x plus 2e to the x dx, which I don't think is going to help me too much here. So, Derek, what were you thinking? What do you? Yeah, that's, whoops. Put that there. The bottom on this one is the same as e to the x plus 1 squared. Because it's FOIL. So if you FOILed that thing out, you have e to the x times e to the x, which is e to the 2x, plus outers and inners would be 2e to the x plus 1. And when you do that, then it's fair. Then it's pretty easy. You would let u equal what? You'd let u equal e to the x plus 1. And then you get e to the x dx, which is that top part. So our new integral would be a du, be 1 over u squared, which is u to the negative 2. Right? Which is a power rule. Raise it up 1, divide by negative 1, and so we get negative 1 u to the negative 1 plus c, which would be negative 1 over e to the x plus 1. Right? Negative 1 over u, which would be that. But again, you had to be able to see that. So that was kind of tricky. Okay, what else? 59. Okay. 59, is that the one that says x and then, or is it the one in the packet? Is it the one in the book?
Yeah.
X tangent x squared dx. So we let u equal what? X squared. Okay, and the nice thing about that is the du is going to be an x dx, right? Which is sitting right there. Of course, there's a 2 there, which we can move around. So we get 1/2 du equals x dx. So when we get this all out of there, we'd have tangent u, the x dx. We got 1/2 there. Oops. Du. And then the antiderivative tangent is what?
Okay, I just didn't know if after you got to that place you could still do what you did, like how you did.
Yes.
Okay.
Now, yesterday we talked about, because we did tangent yesterday, right? And I said you could memorize it, right? Tangent, the antiderivative tangent is negative ln of absolute value of cosine x plus c, right? So if you memorize that, you're in good shape. But there are problems where you have to do u substitution twice, right? I mean, that can happen. So what? How would you do a u substitution again? Well, it wouldn't be u substitution. It'd have to be v substitution or w substitution or something, right? You have to use something else. And so what we could do here is we could say, well, let's do just like yesterday, just so you see it here real quick. You know, so you'd say, well, let V equal cosine U. And then so dV would be negative sine U du, right? And so there's the sine U du, which would be replaced by the dV negative. Am I off the board? Just about. And then, so that'd be dV. And then, what would I be left with? 1 over V. So I get negative 1/2 ln V plus C. And V is cosine U, and U is x squared. So it's negative 1/2 ln absolute value of cosine x squared.
How would you know that cosine though if you didn't do the next
How would you know what?
substitution? The cosine. Isn't it always the cosine?
You mean when I said the negative ln before? You mean, or what?
Yeah, well, like, because what is just tangent? Is it
Tangent
negative L?
is negative ln absolute value of cosine.
Oh, okay.
That's what it is.
Okay.
Yeah, that's what it is. Okay? All right. So a double substitution. Now, that's a good one to talk about because we're going to learn a new technique today, and it's possible that we'll have problems where we do the new technique we have today, and then we'll get to a certain point in that technique, and then we'll have to do U substitution in it. Or there are problems where we start out with U substitution, and our new integral needs the new technique we're going to learn today. In other words, remember what U substitution is all about. U substitution is simply saying, hey, here's an integral we don't know how to do the antiderivative of. U substitution turns it into a new integral that hopefully we can do the antiderivative of. Now, right now we have really only one way to do an antiderivative, and that's a basic antiderivative. The only ones we really know how to do the antiderivative of are on page 333. Right? Now, there's more that we could memorize than that, tangent being one of them. Right? If you want to memorize the antiderivative tangent, fine. Right? But really, the only things we know how to do the antiderivative of are those ones on page 333. U substitution just turns our integral into one of those. Well, that's the same with this new technique. This new technique today is going to be, here's an integral we don't know how to do, let's turn it into something we do know how to do. Now that might mean we turn it into something where we can do U substitution, which turns it into something, you know what I mean? I mean, that's the whole process in doing these things. Now, I will make one other comment here because I've had several people ask me about this. The more basic antiderivatives that you can kind of do in your head. Now, I know we only have the ones on page 333, but let's think about this for a second, because this has come up from several. Okay, there we go. This has come up from several people that have asked me this. If I have this problem right here, okay, what is the antiderivative of that? Do we need U substitution, or can you just do this in your head as a basic one? Or both? Could I do this as a U substitution? Yes, but it wouldn't be necessary. What is the antiderivative here? 1/2 e to the 2x plus c. Because when we do the derivative of e to the 2x, we have to kick out a 2. When we do the antiderivative, we kick out a 1/2, right? And we had learned that early on with antiderivatives. Now, the problem people run into, though, and I've had several people ask me about this, is they think that'll carry over to this. Now, with derivative, it was pretty similar. With derivative on this one, if you have e to the 2x, you kick out a 2, right? And so it makes sense that when you put a 1/2 there, that'll take care of that. Because when we check our answer, do the derivative, we'll kick out a 2, it'll cancel 1/2. Well, I've had a number of people tell me that they think, well, on this problem, wouldn't you just go e to the x squared and kick out a what? You know what I'm thinking of? A 1 over 2x. If in a derivative you have to kick out a 2x, on an antiderivative you kick out a 1 over 2x. That way it'll cancel the 2x. Well, unfortunately that doesn't work, does it? Because if you're going to do the derivative of this, what do you have to do? Product slash quotient rule, right? And so the derivative of this does not come back and equal this. So this is no good. You can't do this. So as soon as you have something on the inside that's got a weird derivative, like with x's in it, then that doesn't work. But if you've just got a 2 in there, a constant in there, you can do just a basic antiderivative. And if you can handle that, you're ahead of the game. Here's another one. This would be one that some people were asking me about. It's similar to this. If I got the antiderivative of 3x plus 2 to the 5th dx, do I need to do a u substitution on that? Couldn't I just go to a power rule right now? Right? This would be 3x plus 2 to the 6th times 1/6, right? Or divide by 6. Also, I have to kick out a 1/3. That will do it. Now, some people won't be comfortable with that, and so I could do a u substitution, which would be u equals what? 3x plus 2. The du would be 3 dx. Of course, we know the 3 will move over to the other side, and sure enough, that's where that 1/3 comes from. But if I had a 3x here, you can't move a 3x over to the other side, right? Like a 1 over 3x. And so that's why this won't work. And so, of course, when we do our substitution, we get a 1/3. We get u to the 5th. So now we raise the power up and divide by 6. And you can see we'll get a 1/3 and a 1/6, then a u to the 6th, which is this. Okay? So I wanted to make sure, because I was getting several questions about that, about when you could then do the power rule, or if you had to do a u substitution or whatever. Okay, here's another one. This is on the LH packet number 24. This has stumped quite a few of you. It's this one right here, number 24. And people are trying to figure out what to let u equal and so forth. Do you need u substitution on this problem? Right? Every once in a while, we're going to throw in one that is really just a basic antiderivative with maybe some constants thrown in. Here, all you have to do is pull out the 1/2. You're left with x to the 1/2 on the bottom, which is x to the negative 1/2. That's just a power rule. Right? Now, it's kind of funny because, so now you just do your power rule and you get your answer. But I had somebody do this. I'm not going to name any names. But somebody did this. Somebody said, well, I'm going to let u equal x. Now, what do we say about letting u equal x? There's no sense of doing it. Now, I probably made it sound worse than it was. It's not like don't do it. But if you do it, in my mind, it doesn't do you any good, right? Because the derivative is that. And so when I substitute, I get 1 over 2 u to the 1/2 du. Now, so why shouldn't I have done it? It doesn't change anything. It's the same thing. But for this person, it was kind of funny. This person, they looked at this, didn't know what to do. They did this substitution, got to here, and then they said, oh, that's just this. And then I can do a power rule, and they did it, and then they substituted the x back in, and they got the answer. So for them, it actually worked. For some reason, they were able to see that this was doable, but they couldn't see that this was doable. So whatever, that's fine. It worked for them. It worked for them. So I guess from that standpoint, you could do that. But so those are just some of the kind of crazy things we've seen. Does somebody have another one? Because I've got one we could do. Yeah, Alex?
43 in the packet.
43 in the packet. Okay. I think that's one of those solve for X ones, isn't it?
Yeah.
That's why I turned that on there, so you guys can help me out with that. Okay, what's your question, Alex, on that one? What'd you let u equal?
I don't know. I think I have a problem with the x substitution.
Okay,
Well,
this will be a good one because this leads into the other one that I want to do here. So what do you let u equal?
I had u equal x plus 2.
That's a good choice. And then the du would be
Dx.
dx. Okay? So now my substitution, this would be u to the 1/2, right? The square root part. So that part is u to the 1/2. The dx is equal to du. So that's du. That'll come out as du. And so now I've got this extra x here, What did we say about that x?
So,
Solve for x here, and we get x is u minus 2. So in place of the x, we put u minus 2. Now what advantage is this over this? We can distribute. In this one, we cannot distribute this x through the square root. We can't distribute an x through a power, but here we can distribute. Now this is another problem I've had people ask me about. They want to do the antiderivative right here. No, that's a product. We can't do that, right? We can't do the derivative of this or the antiderivative of this. But we can distribute that through. So that's u to the 3/2 minus 2u to the 1/2 du. Now notice I haven't done an antiderivative. This is another thing I see people do is they take off the antiderivative symbol because they're doing all this adding of powers and they think they're doing an antiderivative, but all you're doing is algebra. Alex, does that make sense? Once you get to here, now you can just do your power. Okay? So we raise that up, it'd be 2/5 u to the 5/2 minus, raise it up to 3/2, that'd be 2/3 times 2 would be 4/3 u to the 3/2 plus c. And then, of course, put your x plus 2 back in for the u.
Because that's what I got, but I thought I tried it on the calculator. And it was wrong.
Well, again, you get into the calculator ones, and then you try to see what they got, and they write it differently, and so then you try to see if they're equal, and then, you know, so I wouldn't be too concerned. I mean, obviously, you want your answer to match with the calculator, but some of these really kind of weird ones with fractional powers, it's hard to understand exactly how the calculator's doing it. Here's the one I wanted to look at. Very closely related to this one. It's number 36 in the book, and I think it's also number 65 in the book. And I don't know if you tried them. But let's go ahead and do number 65 because that's very similar to the one we just did here. Okay, number 65 in the book says this. Oh, also, I might make this comment, and I don't know if we're going to get into one of these, but whenever you see a 1 plus x squared on the bottom, you think of what? One of the things you think of. Arctangent, right? If you get a 1 plus x squared or 1 plus u squared, that's an arctangent. Don't forget about this one. We haven't done very many of these. What about when you get that on the bottom? That's arcsine. So whenever you see one of those two kinds of things on the bottom, that's something to think about. Now, it's not always an arcsine or an arctangent, but it could be. So it's something to keep in mind. Yes?
The x squared plus 2 is a square root.
So that would be to the 1/2. Okay. So we have the same concern as the one Alex asked about. We cannot distribute the x cubed through there because of that power, because of the square root. So what is your thought? What would be, there'd be two thoughts I could see of what to use for u here.
X squared plus 2.
The inside, right? For sure. But then I could see you thinking a step ahead and saying, yeah, but the u is 2x dx, and I don't have an x dx there. And so I have had people choose x cubed as the u. Because they're thinking, well, the du would be 3x squared dx, and there is an x squared in there. Unfortunately, is there an x squared dx in there? There's not an x squared dx. There's an x squared, but it's in with the 2, and then a square root, and then the dx, and so that's a whole different thing. So x cubed would not be a good u to pick. What you want to pick is x squared plus 2. Let's see where this takes us. So we go, and this is about our only choice. Now, you say, you know, what about today when we learn this new technique? How am I going to tell if I should go down the road of u substitution versus this new technique? Well, I think you'll find that the new technique we learned today, they look quite a bit different. And hopefully you've done enough practice with u substitution that you're going to feel pretty comfortable knowing, hey, this one looks like a u substitution. You know, you can think a step or two ahead and you have a good sense of it. You might not have so much on this one, but I think once you see this, you'll see that it makes some sense. So we do our du, we get 2x dx, move the 2 over, as we often do. It's not in there. We go to make our substitution. And this subs out easily enough. That's u to the 1/2. Now here's the problem. We don't have an x dx. Zach?
Can't you split up the x cubed so it's x squared and x and then
Exact. Did we talk about that yesterday? No, okay. Now, we did have one yesterday where we had an x plus 4. Remember that one where we had x plus 4, and then we had a 1 plus x squared on the bottom? And we said we could split that into two separate integrals. Now that's different. See, in that one, some of you tried to do u equals 1 plus x squared. The du is 2x dx, and you said, well, you got an x dx sorted here with this plus 4. Well, the plus causes a problem. Plus is an issue because it's x times dx, essentially, is what we have. And so this is not an x dx, and we can't get a plus 4 in there. But with times, that's a little different. X cubed dx, I could write that as x squared times x dx, like that. That's my x cubed. Now I can look at this and say, okay, that part right there, that x dx, I can sub out as a 1/2 du. That's perfectly fine. So what that leaves me with is an x squared unaccounted for. Well, what's x squared? Right here, you can see that x squared is u minus 2. So in place of the x squared, I can now put u minus 2. And again, we see that same thing has happened. We went from a problem where we couldn't distribute to a problem where we can distribute. And so now we run that through. We get, what's that?
Same.
Yeah,
Same as one.
it's the exact same.
Oh, it's the exact. Oh, yeah, it is the exact same thing. Except our u is different
Right.
by that much, right? I mean, hardly anything. So I won't finish it past here. But again, same thing. So you look at that problem. You look at that problem, very similar with the square root, except for the x squared and the x cubed in there. But finish it from there, plug them back in. All right. So we've done a lot of them here with some algebra. We did a little bit with trig earlier. We did that first one with e to the x. You know, on the 10 gateway test questions, my guess is 6 of them, in the ballpark, half or a little more than half would be u substitution. I mean, that's a big one. It's kind of like chain rule. Chain rule shows up in a lot of derivatives we do. On the last gateway test, you had 1 or 2 of that implicit differentiation. Remember that? Well, there'll probably be, it's kind of the same thing. It's probably going to be a few basic antiderivatives, maybe be a bunch of u substitution, and then a few of this new technique we're going to talk about today. Okay? And some of the harder ones might involve combinations of both or something like that. Okay, well, let's go ahead and move on to that new technique then, so we can give you some support time here on this. And the new technique is called integration by parts. Okay, it's called integration by parts, and what that means, again, it's the same idea. We want to take our integral that we're trying to do, and we're going to turn it into a new integral that's easier to do, which is the same thing u substitution tried to do. All right, and what we're going to do is we'll break it into parts, so therefore the name. Now, it comes from the product rule. All right, so we're going to go ahead and develop this formula. You'll never have to do this again after we do it today. But you'll have to just memorize the formula we come up with. But I'd like you to see where it comes from. So it comes from the product rule. Just like u substitution is kind of an offshoot of the chain rule. So the product rule is this. Okay, derivative with respect to x of u times v. Remember, u and v are just functions of x. Just like in u substitution, u is a function of x. Like we let u equal x plus 2. We let u equal x squared. We let u equal sine x. U is some function of x. Same thing here. U and v are functions of x. Now, that's the derivative with respect to x equals this. So what we want to do is add in reverse. So we want to do the antiderivative. So I'm going to do the antiderivative of both sides with respect to x. Okay, which means I want to do this. I want to do this to both sides. Well, what's the antiderivative of the derivative? In other words, what do we get on the left side? We should just get uv on this side, right? They should just cancel each other out. Okay? And I want to do the antiderivative of this side. Now it's a plus, so I'm going to do the antiderivative of both of them individually with respect to x. So this one's going to be integral u prime v dx plus integral uv prime dx. So I'm doing the antiderivative of both sides with respect to x. Now, because of the notation, I want to, instead of writing u prime, I want to write Leibniz notation, which would be what? For u prime. du over dx v dx. Okay, so I'm just going to write u prime. Instead of u prime, I'm going to write it du over dx. Same thing. And here we'd have u, and v prime would be dv dx dx. And of course, what jumps out at you? Dx is canceled. Dx is canceled. And we get uv equals the integral, and then I kind of rearrange it, v du plus the integral u dv. Right? And now I'm going to solve for this integral, u dv, by subtracting this one over. So our final formula, and the one that you will have to memorize, says this. The integral of u dv is equal to uv minus the integral of v du. Okay? Now, what does that mean? Well, this side over here is our original integral. That's the integral that's in the problem. So we're going to break that into two parts. There's the u part and the dv part. Okay, that's why it gets its name by parts. And what we're going to do is we're going to take that original integral and we're going to rewrite it as that, which is another integral, but hopefully that integral will be easier to do than the original. Okay? So, how's that look? Well, let's do a few examples. X times e to the x dx. Now, let's say that you were presented with this one and you did not know the new technique yet. Right? All you had was u substitution. Well, what do we have? Basic antiderivatives and u substitution. It's clearly not a basic antiderivative, so what would you try? U equals x wouldn't work very good, right? How about u equals, I mean, that'd be about your only option, but then you say, but then I have an extra x sitting there. Oh, well, we've dealt with extra x's, right? How to deal with an extra x, so we'll solve for x thing. So you might think, well, I'll let u equal e to the x. Don't write this down yet, please. But, so you might do that. And if you were thinking clearly, you would realize that e to the x dx is just the du. You wouldn't substitute a u there. You just do that. So you would look at this and say, okay, e to the x dx, that's just du. And then x, you have to solve for x. Well, what do you get if you solve this for x? You get natural log. You do natural log on both sides, so it'd be natural log of u. So you substitute that in for the x, you get natural log of u. Now, do we know the antiderivative of natural log? We know the derivative, but we don't know the anti. It's kind of like tangent, right? Now, tangent, we were able to do sine over cosine and get it. But unfortunately, to get the antiderivative of natural log, guess what you need? Integration by parts. Okay? Well, if you already knew integration by parts, you would have used this in the first place on this problem anyway. So, u substitution doesn't work. Now, sometimes it's a very fine line between what will work with u substitution and what won't. For example, what if this problem was this? What would you do? You'd let u equal x squared, because then the du is 2x dx. See, so hopefully you're to the point where you would look at a problem like this and you would right away, if this was on the gateway, you would look at that and you'd think u substitution. I'll let u equal x squared. The du is the x dx set right there. This is great. This is a perfect u substitution problem. But if I change that to just an x, now it's not. Now Now it's not. Okay, so here's how this is going to work. What we want to do is we want to rewrite our original integral in terms of a u and a dv. Now, not all of you have been following how I show my work on the u substitution, which is fine, you know. But you might want to do it on this one because it's pretty easy to get kind of confused with all the stuff. So here's how I usually do this. We're going to have u equals something, and we're going to have dv equals something. Okay, so it starts out kind of like u substitution. You know, where we pick a u. Well, in this case, we're going to pick a u, and we're going to pick a dv. Now, the dv always has the dx in it. Okay? The question is, what do we pick for u? Do we want to pick x, or do we want to pick e to the x? Now, we're going to find out which here in a little bit. But just to start, we're going to go ahead and let u equal x. And we're going to let dv equal e to the x dx, or all the rest of it. Now, everything has to be accounted for, just like in regular u substitution. We got to take everything that's in the original, and it's got to show up here. All right, now what do you suppose we do with the u then? We do du, right, which means derivative. Now, what's the derivative of x? 1 dx, right, which we usually just write dx. And what do you suppose we want to do with the dv? We want to find v. Because if you look at the right side of our formula, we need v in two different places. Well, if you have dv, to get to v, you're going to do the antiderivative. So in this case, in u substitution, you had to do a derivative to get the du, and then at the end you did antiderivative. In this case, we're going to do both in this step. We're going to do a du, the derivative for that, or we're going to do an antiderivative for this. So now, that might be our first clue as to what we want to do, is our u, we might want to pick something that's easy to do the derivative of, and our dv, we might want something that's easy to do the antiderivative of, right? Now, in this case, they're both pretty easy to do derivative or antiderivative, so it may not matter, but we'll see. What's the antiderivative? E to the x, and we don't put a plus c at this point. Plus c will just come in at the end. Plus c will just come in at the end. So we just do that. All right, and now, once we've done that, all we do is follow the formula. We just fill in the right side of the formula. So we take u times v, so that'd be x e to the x, right? U times v, minus the integral of v, which is e to the x, du, which is dx. And look what happened, just what we wanted. We got ourselves a new integral that is easy to do. So we write down our x e to the x. What's the antiderivative of e to the x? E to the x plus c. All right? Now, don't write this part down, but what if we would have done that backwards? What if we would have let the u equal the e to the x and the dv be the e to the x, or the x? Watch what happens. The du would be e to the x dx. The v would be 1/2 x squared, right? When we go to write our formula, we'd have u times v, so e to the x times 1/2 x squared minus the integral of v 1/2 x squared du, which is e to the x dx, right? We were hoping to turn our integral into something easier to do. What happened? Harder to do, right? We got an integral that's actually harder to do. Now let's investigate why that happened. We said a minute ago that we're going to want a u that's easy to do the derivative, and we're going to want a dv that's easy to do the antiderivative. They were both pretty easy. Well, the key is going to be the one that's the antiderivative. We want one that's going to be the easiest to do the antiderivative. Well, it doesn't get any easier than e to the x, right? I mean, it's just its own antiderivative. As far as doing a derivative, x, really easy to do a derivative, it's just 1. To do an antiderivative, it's easy to do, but it gets messier, right? So you start thinking about the different functions. One of the traits of integration by parts is you get functions that are, your integrals will have different families of functions in it. There'll be a mixture. There'll be some exponential, some log, some algebra, some trig. So what we're going to do is make a list of what things are easiest to do the derivative of and hard to do the antiderivative of, and those would be the ones we'd want to pick for our u. Those would be our first choices of what to pick for our U. Let me say that again. For U, we're going to want stuff that's easy to do the derivative of and hard to do the antiderivative of. Give me an example of a function that comes to mind that fits that. Easy to do the derivative, hard to do the antiderivative. Natural log. We just talked about it a minute ago, didn't we? Natural log, we don't even know what the antiderivative of that is. But the derivative is very easy. So that's first on our list. We're going to put L for log. We're going to put L for log. We're going to come up with an acronym here, kind of like PEMDAS, kind of like Please Excuse My Dear Aunt Sally. And this acronym is going to help us know what order to do things. So log is first. Easy to do the derivative. We don't know what the antiderivative is, so we certainly don't want log to be a dv. Ever.
The G didn't show up.
Okay, what else? What's another function family that we do not know an antiderivative of? Or is hard to do an antiderivative of?
The arc sine.
Arc sines and arc cosines, we have no idea what those antiderivatives are. But we do know they're derivatives. So that's going to come second. I'm going to put an I for inverse trig. Inverse trig. And I'm running out of room, so I'm going to rewrite it over here. Okay. All right. So log and inverse trig. Those are our first choices for U because we don't want those to be the dv. All right, what else? Well, we're running out. The only ones we have left are the trig functions, the exponential functions, and algebra functions like x squared. What do you suppose should come next? Out of those three, algebra functions probably are kind of 50-50. You know, they're pretty easy to do both ways. Okay? So we're going to do algebra next. So A for algebra. Like an x squared, next to the 1/2, something like that. Okay, next is going to be trig, sines and cosines. Nice thing about sine is the derivative is cosine, but the antiderivative is a negative cosine. I mean, they're kind of the same. Okay, so we can use those either way. And the last one is exponential, e to the x. And the nice thing about exponential is they're very simple to do derivative, but they're very simple to do antiderivative, and not everything's simple to do antiderivative. So here's what this Liate is. This is how to pick U. That's what Liate is. How to pick the U. Once you pick the U, the dv is everything else that's left. Once you pick the U, the dv is everything that's left. All right, Liate. So let's do this one.
You make that up.
I did not make that up.
I mean, not make that up, but I mean, think of that up.
I didn't even think of it on my own. I think it might be in your book. I'd heard of it before. I mean, I did it. I mean, my teacher showed us that. I think it's been around a long time. Yeah, here it is at the bottom of page like 461. We have to jump clear to chapter 8, by the way, for this stuff. Okay. Yeah, well, here's the thing. Most of these integration techniques are in Calc 2. Use substitutions usually in Calc 1. But this stuff we're getting into now is kind of right towards the end of Calc 1. We're getting into some other, there's some other things that will be Calc 1 yet, but then we kind of start getting into Calc 2. So the AP test will have use substitution on it, basic antiderivatives. The AP test does not have integration by parts. Okay? That's what we're going to do. All right. We're not going to get into as harder ones as we do with use substitution. All right, so here's the next one I want you to do. X squared ln x dx. Okay? X squared ln x dx. All right. There's no clear U substitution, right? I mean, you might end up trying some things, that'll be a road you'll go down and you'll get stuck, right, so you come back. It's integration by parts. Now another hit on the integration by parts is, well, I think I said it earlier, but may not have registered. It's a mixture of function families. If you look at the homework we've been doing, most of the integrals have just x's and algebra stuff in them, or they just have e to the x's in them, or they just have log in them, or they just have tangent or sine or cosine in them, right? When you get a mixture of the function families, then that's a tip anyway that integration by parts might be involved. All right, what are we going to pick for u? ln x, Liate, log always comes first. dv then is what's left, x squared dx. So, du is 1 over x dx, and v is 1/3 x cubed plus a c. Okay, but don't put the plus c. Don't put, I'm sorry. I said plus c, I meant to say don't put the plus c. All right, so we get that, but I like the fact you were thinking there should be a plus c because you were doing antiderivative. So we follow the formula, which is u times v, 1/3 x cubed times ln x, minus the integral. Notice there's no integral on that first one. It's just u times v, minus the integral of v, 1/3. Now I could have put that 1/3 out in front. V, which is 1/3 x cubed, times du, which is 1 over x dx. Then what? Cancel an x, absolutely. Do not try to do antiderivatives right now. You cannot do the antiderivative of this and the antiderivative of this. You can't do an antiderivative product that way. It does not work. You have to see that that will simplify into 1/3 x squared. You have to see that. And so we accomplished what we wanted. We got a new integral that's now easy to do. It's a straight power rule. So we raise that up to a 3. Divide by 3. We already have a 1/3 there, so what are we going to have? We're going to have a 1/9 x cubed plus c, and then don't forget to bring down the rest of them. Somebody in here is going to miss one on the gateway test because you're going to do all that work and then you're going to forget to bring down the uv part. Oh, whoops. That was just a big multiply sign. It's a long multiply. All right, very quickly. One more. There are a couple of things that can happen along the way. The two I just showed you are basic run-of-the-mill integration by parts. Okay? Liate, you pick your u, the rest is dv, you go through the process, and some of your homework, a lot of your homework will just be practice on that basic part. You'll have to keep track of this minus sign, that becomes an issue sometimes. I mean, there's just a lot of little things you can get thrown off on, so you gotta practice that. But here we go. We just got in saying we don't know how to do the antiderivative of arctangent. Just like with tangent, we didn't know how to do the derivative, so we did a u substitution. We made it sine over cosine, and we were able to do it. Okay? We were able to do it. Well, we're going to do the same thing here. Now, again, u substitution wouldn't help any. If we try to let u equal arctangent x, it's, nothing to do. We can't do arc sine over arc cosine. That doesn't work. So we're going to do Liate, and we're going to pick our u. Well, arctangent is an inverse trig. It comes very early in the acronym, so we're going to pick that for our u. So we're going to let u equal arctangent. I mean, plus, the whole point is we don't know how to do the antiderivative of arctangent, so you certainly wouldn't want it to be dv, because that's what you have to do. So dv is just dx. That's all that's left. So what is du? 1 over 1 plus x squared dx. Right there.
Can I speak with Kelly Warren for just a second?
Kelly is in, yeah,
401.
401.
Thank you very much.
Sure.
Sorry to interrupt.
So, antiderivative,
Yeah.
that's terrible.
I know, I was like.
It's February and okay, anyway, what's the antiderivative? How do you say his last name? Mr. Weber. All right. What's the antiderivative of what? Yeah, it's just 1, right? It's 1 dx. Antiderivative is x. Okay? V equals x. So, we go through our process. X, arctangent x, u times v, minus the integral of v du. Now look at that a minute. V du. Now how would you write it? X over. A lot of times the way you write it is helpful. Okay? Is that an integral we can do? It's not a basic antiderivative, but it's a u substitution. Remember earlier I said, here we got one where we do an integration by parts. The whole idea is to turn it into a new integral that we can do. That might mean it's one we have to do with u substitution, and it might work in reverse. We will now have some problems, probably, where you do a u substitution, it gives you into a new integral that now needs integration by parts. So it could work both ways. So, of course, we shouldn't probably do a u substitution because we already called u arctangent. So, you could, as long as you keep track. Yeah, as long as you don't confuse it, you can. But what you'll see in the books, a lot of times they'll do w. We already use u and v, so we'll use w. So what would you let w equal? 1 plus x squared. And dw, other than being a character in some... Arthur, yeah, Arthur. dw would be 2x dx, move the 2 over, right, which takes care of the x dx. So that integral would be a 1/2 a dw, 1 over u, which is natural log. So this would be 1/2 natural log of u plus c, no, not u, w, yeah,
Oh.
2 u's. So, is that what it is? I don't know. Is that word its name? I think so. W, 2 u's. W, all right. That's the best thing. It's not only the only, it might be the only thing, and it's the funnest thing. And all right, anyway. X, arctangent x, minus 1/2 ln, and w was 1 plus x squared plus c. And of course, this would also be one where you wouldn't need the absolute value bars because 1 plus x squared is always positive. So you wouldn't have to have the bars there, but they're okay to have. Right? Okay. So, for your homework, on the packet, all right, or on the assignment, not the packet, I'm sorry, on the assignment sheet, now I'm gonna kind of jump around here a little bit, so I'll just write it down. 8.1 in your book. 8.1 in your book. There's about 7, 8 problems here. Maybe 10. 9 through 11. 15 through 20. And 31. Then we're going to jump into the LH packet for some more U substitution practice. Okay. So, all right, on page 310, we'll do 45 and 59. I think 59 is a definite integral, so don't forget to be doing some definite integral. And remind me on Friday, maybe we can practice one of those. We'll spend a lot of time practicing these things on Friday. 45 and 59. Also in the LH, page 341. Now, the LH packet's broken up by function family. So the page 310 is mostly algebra kinds of stuff. Page 341, I think, is like exponentials and logs. Or it might be the trig, I don't remember. But it's so on 341, we'll do 26, 28, and 31. And then on LH, page 356, we'll do 62. I think that's the exponential log ones. 62 and 67. So these LH ones should be U substitution. Okay. I mean, it'll be pretty easy because the ones in 8.1 in your book, you know, will be integration by parts. You know, but on Friday we'll practice some where I give you some and you don't know which. You know, you'll have to decide what to use. So do those. That's about 16, 17 problems for tomorrow. All right, go ahead and you can have the last 25 minutes here or so to work. And right at the end, I'll pass out the paper assignment so you can take that home with you and begin looking at that a little bit. Yes. 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 The only thing new we really have to talk about is just a couple of other things that can happen to you on integration by parts, a couple of kind of weird things that can come up. Oh, don't forget to create an account on Turnitin.com.